Now let us begin our part 2. Please see, from the part 1 we have already found out the displacement of the block M. We have already found it out. If we are able to find the acceleration of the block M, we can use the equation v square equal to u square plus 2as to get the value of v, as u is 0, s we already computed from the previous example or from the previous topic, that it is m into h upon m plus n tan theta. So all that is left to be found is the value of acceleration of this wedge. Now let us try to understand some sign conventions. Let us take v as the relative velocity of this block as it slides down. So the acceleration of this block is g sine theta in the downward direction. But that is not the only force acting on it, because this block, this wedge is moving to the left. It is having an acceleration am, and this acceleration am will have a component. You can see this angle is theta, this angle is also theta, because they are corresponding angles, and the acceleration will have a component am into cos theta. So what is the relative acceleration of this block? The relative acceleration of the small block is given by g sine theta minus am cos theta. As you can see, it is in the opposite direction, and the relative acceleration is given by g sine theta plus am into cos theta. This is the relative acceleration of the smaller block. As no external force is acting, we also have to consider the conservation of angular momentum. But before that, let us again apply some sign conventions and some terms. V small m is the actual velocity of small block. V capital M is the actual velocity of the wedge whose mass is m. Let us apply the relative velocity term in the horizontal direction. You can see here, if v is the relative velocity, then in the horizontal direction the relative velocity will be given by v cos theta. The relative velocity of the block with respect to other block is given by the actual velocity of the block small m minus actual velocity of the block capital M. But as the velocity of block capital M is to the left, it will become minus, and I will have the relative velocity as Vm plus V capital M, and that gives me the actual velocity of the small block as V cos theta minus V capital M. This is the actual velocity of the smaller block as it is coming down. V is the relative velocity of the smaller block. Vm is the actual velocity of the wedge. Now we are going to apply the principle of conservation of linear momentum. Mass of the small block into velocity of small block must be equal to mass of the mass of the wedge, that is capital M, into velocity of the wedge, which is V capital M. Obviously, as one is to the left and one is to the right. Let me substitute Vm in this equation, and I get m into V cos theta minus Vm is equal to capital M into V. I am going to take the derivative with respect to time, so that the derivative of V becomes acceleration. Derivative of Vm also becomes acceleration. As you can see that V cos theta is the relative velocity. The derivative of relative velocity will be the relative acceleration ARm. So let me do that. So it is m into ARm cos theta minus A capital M. It's capital M as it is, and derivative of Vm is again A into capital M. Now I am going to substitute ARn from this into this. And see what I get. I get M into, I am going to substitute for ARn, but before that let me simplify this. M into ARn into cos theta minus M into AM is capital M into M. That is M cos theta. I am putting MRN now, which is G sin theta plus AM cos theta minus M into AM. It's capital M into A capital M. Please note this is small m. Now let me simplify this. I get Gm into cos theta sin theta plus Am into cos square theta into small m minus M into Am is equal to capital M into A. Let me take all the capital M to the right and I get G into M into cos theta into sin theta is capital M into Am plus small m into Am minus small m into cos square theta into Am. Let me take A capital M common from this, and what remains is capital M plus small m minus M cos square theta. If you take M common, 1 minus cos square theta will be equal to sin square theta, and so I get the final answer. I will write here as mg into cos theta sin theta is equal to Am into capital M plus small m into sin square theta, and that gives me the final acceleration Am as mg sin theta cos theta upon capital M plus small m into sin square theta. Now you can understand we have S, we have Am, and we have this equation. Using these three terms, I can easily find now the velocity of the wedge as the block has moved up to this distance. So let us move to the final part of our calculation. I understand it's a very complicated sum and we need to have some patience. So let us come to the final part, that is v square equal to u square plus 2am into s. U is initial velocity, which is 0, to what is am? It is mg into sin theta into cos theta upon capital M plus small m into sin square theta into, what is the displacement here? It's mh upon capital M plus small m, and for tan theta, let me write sin upon cos. Now see what will cancel here. It's sin term will cancel, cos term will go up, and I will get 2 m into m is m square g h. One cos theta is here, one more cos theta goes up, becomes cos square theta upon m plus small m into sin square theta into capital M plus small m. This is the value of v square. Obviously, the velocity will be square root of the entire term. So velocity will be this entire term raised to half. So this is the final answer of our problem. Let us quickly summarize. In part 1, first we found the distance moved by the wedge as the block comes from top to bottom. For that we use the principle of conservation of momentum, and we also considered that the center of mass does not move when there is no external force acting, as in this case. From that, we got the value of the distance moved this time. Then we went on to find the relative velocity. From the relative velocity, we computed the acceleration of the block M, which is am, and then finally we use both these results into the Newton's equation of motion and got the final velocity v. I understand the problem is complicated. Please read it and see it again and again so that you can understand the complexity.